Dear students, in today's lecture, we will discuss about the transformers, the electrical transformers basically. So this lecture will cover the introduction to the electrical transformers. We will also understand the working of the transformers and then construction, how these transformers are made, constructed, and then eventually we will discuss about the ideal transformer. What is an ideal transformer? Now, let us start with the transformers introduction. Now, what is a transformer basically? As the name implies, transformer. This is something which transforms. Now, what does it transforms? It transforms the electricity, transforms the voltage from one level to the another level. So this level may be either it steps up the trans voltage or it steps down the voltage. So when we say step up the voltage, that means the voltage is increased, and when we say step down, that means the voltage is decreased, reduced, and increased, right? So an electrical transformer is an electromagnetic device which is used to transform the voltage. It transforms the voltage. It does not change the voltage. It changes the level of the voltage. It does not change the nature of the voltage, right? So from one level to another level. So the level is either step up or step down. But the one thing which you have to remember is at constant frequency. That means it does not change the frequency of the signal, supply, or voltage. That remains same. Right now, as you can see in these diagrams here, these two diagrams are drawn here, shown here in this slide, right? So what happens in a transformer actually is that when you provide supply to one of its windings, which is known as primary winding, so because of the Faraday's law of electromagnetic induction, um, the flux is generated here at this end. The direction of flux can be obtained by using right hand thumb rule, right? So so the flux will flow and it will circulate in this particular iron core. This is iron core, right? Now because of the mutual induction, okay, the same flux is linking with the another winding, and we know when the flux is linked with the winding, and EMF is induced in the winding, and the load is connected at this particular end of the transformer. So what actually happens, the level of the voltage at this end and the level of the voltage at this end is different generally in the transformers. So either V1 is greater than V2 or V1 is less than V2. So in this case, this we call as up transformer, and this we call as step down transformer. Remember one thing, a transformer does not change the nature of the voltage. Okay, the nature of the voltage at input is AC, and at output also it remains AC. It does not become any other voltage. Neither it changes the frequency of the signal. Whatever frequency of the signal is at the input, the same frequency of the signal is at the output also, right? So how does it work basically? It works on the Faraday's law of electromagnetic induction. This is very clear. Now, if in detail we have to understand what is the working of this device. Uh, now, what happens actually when you give an AC supply to this winding? This AC supply, because this supply is a bidirectional supply at the input, this is a voltage. Now this bidirectional supply, what it does, it generates a bidirectional flux, right? So this bidirectional flux when links with the another winding, so because of the mutual induction, some EMF will induced in this particular winding. Now this EMF which is induced here depends upon the flux which is generated by the primary winding. So there are two things which you need to understand. The first is in the primary winding there is self-induction, and in this we have the mutual induction. right? Now, this self-induction, what it does, it generates an EMF in the primary winding also, and the flux is generated here and it is linked with the secondary winding, and EMF is generated in the secondary winding because of mutual induction. The two windings are not in direct contact with one another. Rather, they are, right, they are mutually linked through flux. So it is the flux which is linking the two windings. They are not in direct contact with one another. It is the core which is used on which we wound these windings, right? This way, and the core is used to give passage to the flux, so that most of the flux which is generated here at this end of the primary winding remains confined to the iron core. It does not leak out in the air, but it practically is not possible. Some of the flux will definitely leak out in the air, but most of the flux will be confined, will be linked to the iron core only, and that is why maximum flux will link to the secondary winding, right? So let me review this slide. A transformer is something which it is an electrical device which transforms the voltage from one level to another level. It either steps up the voltage or it steps down the voltage, right? Stepping up a voltage means increasing the voltage at the output. Stepping down the voltage means decreasing the voltage level at output, right? Now, the primary winding acts as the input winding. This is the input side and this is the output side, right? So then it works on the Faraday's law of electromagnetic induction. There are two types of inductions which take place in a transformer. One is the self induction which takes place in the primary winding where the supply is connected. Another is the mutual induction which takes place in the secondary winding, which is linking with the primary winding through this particular flux. The nature of flux is bidirectional because the nature of supply which we are providing to the transformer is bidirectional. Now, in this animation, you can see this is a small animation wherein you can see, like, okay, if you take this as the flux and these dots as the currents basically which are flowing, right, in the primary winding, so you can clearly observe that this flux is changing its direction. It is reversing its direction. So it is a bidirectional flux, right? And the direction of the current in the primary and secondary winding is also continuously changing. That means the direct nature of signal here is AC, nature of signal at the output is also AC, and the nature of flux is also AC or bidirectional, right? So you can clearly observe this thing. This is how the flux is circulating in the iron magnetic core in a transformer. Now, there's one thing which you need to know. The primary winding is the one where supply is provided, and secondary winding is the one where the load is connected, right? So let us come to the types of transformer. So there are various categories of the transformers. Basically, there are various ways on which the transformers can be categorized. Some of the common categories of the transformers are like step up and step down transformers, which I just discussed with you. A step up transformer is the one in which the output voltage is greater than the input voltage. You can symbolically see it is symbolically represented here. Okay, the level of the secondary voltage is greater than the level of primary voltage. The primary side is always the input side, and secondary side is always the output side or load side, right? A step down transformer is the one in which the output voltage is always less than the input voltage. Now you can notice one more thing, that in a step-up transformer, the number of turns in the primary winding are less if Np is the number of turns in the primary winding and Ns are the number of turns in the secondary winding. So in this case, Np is less than Ns. But V2 or Vs, S for secondary is always greater than Vp, P for primary. This is what step up transformer is. And in step down transformer, you can notice the number of turns of the primary winding and the number of turns of the secondary winding. So here the number of turns of the primary winding are greater than number of turns of the secondary winding. And the voltage of the secondary winding is always less than the voltage at the primary winding. So this is what step down transformer. So this is on the basis of level of the voltage at output. Then the second category, common category, is whether the transformer is core type transformer or shell type transformer. This is based on the construction of the core, type of core used. So core is that part of the transformer which is used to support the windings in the transformer, right? So this is a core type transformer. You can see this is a simple core, and the windings are wound on the either of these two limbs of the transformer, either here and here, right? Primary and secondary, both windings are used on these two limbs, right? But in a shell type transformer, you can see the windings are wound on the center limb of the transformer. So it forms a parallel circuit. It generally forms a series circuit. Core type transformer forms a series circuit, and shell type transformer forms a parallel magnetic circuit because the flux will get divided in two paths, right? And the windings are wound on the central limb of the transformer. Then there is one more category of the transformer, which are power transformer and distribution transformer. So a power transformer is a high rating, heavy rating transformer, which is generally used at the generating end. It basically acts as an interface between the generator and the grid, distribution grid. So you will not generally find such type of transformer around your area for distribution purpose. This transformer can be seen either on substations or the power generating points like your hydropower stations and all that, right? And then we have a distribution transformer you can see very frequently around you, right? So you can see this at the corner of your colony or somewhere, right? So this is the transformer which is used for the distribution purpose, for distributing the electricity for domestic use or industrial use. It is a low power rating transformer as compared to a power transformer. Then let us come to the construction of the transformer. How the transformer is constructed. See, a transformer basically has three parts, two parts in fact, two parts. The first is windings, and in windings we have primary winding and secondary winding. Then the second part is the core, right? So this is the core, and core is made up of laminated thin sheets, and then we have windings. Windings are wound on the core basically. So this is a core type transformer. In shell type transformer, we have a central limb also where the windings are wound. Okay. In core type transformer, as you can see, the windings are wound on the side limbs of the transformer. And this is the primary winding. You can see primary winding is provided with the AC supply. Secondary winding is the load is connected to the secondary winding. The flux will flow into the core. So these are the two major parts of the transformer. Now, since this is made up of thin laminated sheets, as you can see in this diagram, so the thin laminated sheets are made like this. They are grouped together and they are connected there. Then we get the block of that iron core basically, and then that on that particular iron core, the windings are wound, primary winding and secondary winding. Okay, you can see this one. So initially you can see here, Initially, you can see this is a block of iron, but this is actually made up of very thin laminated sheets. Okay. Now, why do we use laminated sheet? That just to reduce the effect of eddy currents, basically, to reduce eddy currents, right? So a transformer is constructed on this basis. Every transformer will have these two major parts. There are many other subparts also of the transformer, but for this particular topic we only have to concentrate on these two parts, like windings and the core. Basically, the core is used to conduct magnetic flux, and windings are used to transfer the voltage from one level to another level. Now let us come to the ideal transformer. Now, what is an ideal transformer? So, when we talk about some practical magnetic circuit, let us say there is a iron piece and we have some winding wound over it. Some current I is flowing here. So the current will flow like this, and there are n number of turns. This is the north pole, this is the south pole. The flux will be generated here and flux will enter here, right? Now, this is a considering this as a practical case, we will have certain flux which will leak out at this particular end, because here you have an interface of air and the material. Also, you have some flux leakage at this particular point. This is one thing. Second thing is, this is one thing, leakage of flux. Then we have second thing, since this is a wire and this wire is made up of some material, for example copper, right? So copper will, this wire has certain length, it has certain area of cross section, so this wire will have certain resistance which can be obtained by using this formula, right? So that means this wire has certain resistance. Okay, resistance of the windings, right? Now the third thing is, this is an iron piece ferromagnetic material, it has certain permeability. But since the flux is leaking into the air, so that means its permeability is less than infinity. Is not infinity, in fact. The permeability is not infinity here. That means it cannot conduct 100% flux. Okay. Then, because the winding has a resistance, so winding will have, this is the third thing, winding will have certain losses also, like copper losses, which are also known as I square R losses, right? So that means when we talk about the practical aspect of the transformer winding has certain resistance, the flux can leak here at these ends of the transformer. This magnetic core cannot conduct 100% flux because it does not have infinite permeability. Some of the flux will leak out, some of the flux will lose, right, due to many reasons. And because of the resistance of the windings, because of the leakage flux, this particular transformer has losses, right? Now, this is the practical case. So ideally what we say, that a transformer is something which possesses following characteristics. The first characteristic is that the ideal transformer does not have any winding resistance, or you can say the winding of an ideal transformer does not have any resistance. So it is a pure inductor. The winding of the transformer is pure inductor. The second thing is, the core of the ideal transformer has infinite permeability. Practically, the core of the transformer does not have infinite permeability. This means that the whatever flux is generated in the core will be confined to the core itself. It will not leak out in the air. It will not be lost due to any reason. So the core is capable of conducting 100% flux, but practically it is not the case. And third is there is no leakage flux, right? Because the permeability of the core is infinite. So all the flux is confined to the iron core. So the flux will not leak out into the air, right? So there is no leakage flux. So there is no flux loss, magnetic loss, you can say. Then the efficiency of such transformer is 100% because such transformer does not have winding resistance. So no copper losses or I square R losses, no flux loss. So when there is no loss, so efficiency is output upon input. So output will be equal to input. So the efficiency will be 100% in this case because there is no loss. So this is what an ideal transformer is. So in this particular chapter, we have studied about the uh, we have discussed about the transformer, what is a transformer, and what are the various types of transformer also we have seen. What is the nature of the magnetic flux, that also we have seen, we have understood. So again, just to revise this, a transformer is a device which transforms the voltage from one level to another level. It does not change the nature of the voltage, it does not change the frequency of the voltage, that remains same. Transformers are of various categories, various types. We have step up, step down transformer, we have a core type and shell type transformer, we have transformer, we have distribution transformer, then we have an isolation transformer, measurement transformer, current transformer, potential transformer. There are various types of transformer. So practical transformers also always have certain losses, they always have certain leakage of flux, their efficiency is not 100%, their permeability of the core is not infinite. But ideally, if we say a transformer must possess all these characteristics, like there is no winding resistance, there are no losses, there are no I square R losses, there are no flux losses, leakage, magnetic losses, there the permeability is infinite and efficiency will be 100%. So this was all about today's lecture, and thank you so much.